Here, auth and lab point uniformly to management servers around 10.1.0.90 and directory services via a CNAME record. In a live production environment, this centralized resolution ensures both the physical and logical isolation of internal authentication traffic. The final section of the file is crucial, as it precisely defines the security operations architecture. The SIEM, log collector, VPN gateway, and firewall edge are all strictly confined within the internal security isolation zone. Here, subdomains for cybersecurity, intelligence sharing, research, public affairs, and core administration are configured via A records. All these subdomains are sequentially assigned to contiguous internal IP addresses from 10.1.0.106 to 10.1.0.110. By confining these sensitive program endpoints within the private network, the external attack surface is effectively minimized. In a real defense architecture, this fine-grained subdomain allocation facilitates strict microsegmentation and access control policies for different business departments. Next, let's look at this section, which defines the DMZ and artifact repository services. Configured here are the DMZ proxy server and Nexus, which serves as the internal repository for code and artifacts during development. Of particular note is the Bastion host record at the bottom, whose IP points to a different subnet at the 10th of October 2010. 1. In an authentic white hat network defense architecture, the Bastion host serves as the sole authorized gateway connecting the outside world to the core internal network. Paired with the DMZ proxy, this design forces all remote administrative traffic through centralized auditing, significantly strengthening the perimeter protection of internal assets. Finally, we enter the dig command in the terminal to query a specific domain from this range DNS server at IP 192.168.8.161. This end-to-end verification marks the successful completion of the core resolution services within our high-fidelity network simulation environment. In the previous step, we enter the command dig.nsa.gov at 192.168, 8.161 inches the terminal. This command instructs the system to bypass standard internet resolution and query our newly configured range DNS server at 192.168.8.161 directly for nsa.gov. Now, let's look at the resolution report returned in the final image. In the core answer section, nsa.gov successfully returns our pre-configured internal private IP 10.1.0.80. Moreover, the authority section below perfectly lists the spoofed authoritative servers and public IP records of the Akamai CDN edge nodes. This high-fidelity response ensures that the browser or automated scripts on the target host notice absolutely no anomalies, fully believing they are connected to the genuine official website. The additional section gives the IP addresses, glue records, for those NS servers. Query time is 4 milliseconds, indicating the server is on the same LAN. These details confirm our configuration is correct.
Executing this test command against an external domain holds several core technical significance in security and exercises. First, it verifies that the recursive and forwarding functions of the DNS server are fully operational, ensuring it handles public requests alongside local spoofed zones. If this step fails, internal users will lose access to the entire internet except for the specific lab domain, which easily triggers an alarm. Secondly, this reflects the principle of stealth in a high-fidelity environment. A qualified simulation must not achieve its goals by breaking original network connectivity. Finally, this serves as a closed-loop verification of the upstream forwarder servers configured in the named .conf options file at the beginning of the video. Now, the resolution response report for the external domain is displayed on the screen, and the test results are highly ideal. In the call answer section, the server successfully returns 4 genuine public IP addresses belonging to Baidu officially. Meanwhile, the authority section and additional section below list the comprehensive architectural details of the Internet's root name servers. This thoroughly confirms that the DNS server possesses perfect public forwarding capabilities, signifying our high-fidelity simulation network is both highly realistic and flawless. Moving into the troubleshooting phase, we first attempt to ping the domain and a public IP, but the system repeatedly throws an operation not permitted permission error. Subsequently, we try to use the dig command specifying an upstream public DNS, but experience a connection timeout. Indicating no servers could be reached. To resolve the low-level network permission issue, we try using sudo smart u+s to reassign the suid bit to the ping command. We try using sudo chmod u+s to reassign the SUID. To resolve the low-level network permission issue on the correct executable path, now query baidu.com and observe the changes, linking back to our WAN timeout and tunnel isolation findings. We appended the -4 parameter to the end of the options. This parameter forces BIND9 to utilize IPv4 exclusively for network traffic, completely disabling redundant global IPv6 queries. Within simulated ranges lacking IPv6 outbound paths, this optimization eliminates iterative connection attempts and subsequent timeouts, drastically boosting overall resolution responsiveness. After completing the IPv4 only optimization We utilize the ns lookup command to execute a final validation on this range DNS server. As we can see, the server responds instantly, successfully retrieving Baidu's 4 genuine public IP addresses via upstream forwarders